And now, Ned Williams' talk, Attacking Chrome Interprocess Communication, Reliably Finding Bugs to Escape the Chrome Sandbox. He will be talking about finding bugs in the Chrome Interprocess communication in order to escape from the sandbox, using a fuzzing method to enumerate the attack surface of the Chrome Interprocess communication. Ned is a vulnerability researcher. He likes C and C++ vulnerabilities, did research for consoles and browsers, and now started to work on mobile devices. Please welcome him with a huge round of applause.
All right. Hello, everyone. Yeah, my name's Ned, and today I'll be talking about Chrome IPC. And actually, as I was writing this talk, I kind of came up with this idea to make it more useful to everyone. And the way I ended up doing this was by trying to start really general and then kind of going more and more specific, all the way down to the Chrome IPC fuzzing. So if you're really technical, the end will be still interesting. And then if you're new to this stuff, hopefully the beginning part will show some of how to get started. So just a quick overview about me. I've mostly been spending the last several years on low-level vulnerability research. And my particular interest is on any kind of critical bugs, meaning kind of the more severe the individual bug, like the more interesting to me. So I'm trying to kind of solve this problem of, how do we make the bug finding process effective enough to bring out these like really rare hidden bugs? And you will see an example of how to do that by the end. But just an overview, like I've basically worked on 4 things. The first being CTFs, then went to 3DS and Chrome. Now I'm starting on XNU, but just a month ago, so not too much yet. Before we get into it, I just want to give a little recap of what happened since last time. So I was part of the Nintendo hacking talk 2 years ago here, and I presented 2 exploits called sound hacks and fast hacks. And not to go into it too much, but I did want to share like what happened here, because I was actually surprised. I put Google Analytics on the sound hacks website, and I thought like, maybe 1,000 people use it or something, but I just looked at the stats like a couple weeks ago, and then turned out like 800K people used it or something. And then I searched YouTube and found like these huge videos where they were copied. So like I wanted to have a screenshot, but it's copyrighted, so didn't do that. But basically, it looks like something on the order of about 1 million users, which is crazy because this is one of my intro projects, really. So I think like this should show you that you don't have to be all the way up onto Chrome or whatever it is to get into this and do some huge fun project. And then I just wanted to publicly talk about the donations because I had a donation link on the SoundHacks website, and we fortunately received about $1,000 in donations, and then half of that went to the emulator people because they that's how I eventually wrote my exploit for that SoundHacks. So it made sense to repay that. And then the other half went to buying switches for like the toolchain developers who couldn't afford it. And so just wanted to thank everyone who used this or whoever donated, just shout out. So we'll get into the actual meat of the talk. So basically, I want to focus on the bug finding process, not exploitation necessarily, because this topic is pretty well explored, I think. And I think the bug hunting aspect is kind of what's the most prohibitive for people to join in. And when I look at the number of people who I play CTF with who are really good at exploitation, and then a number of like these prolific bug hunters, it just seems like from what I see from how smart people are, there should be more people doing the bug hunting, and I hope that if I can talk about it, more people can come over. So with that, the agenda will be just, overall, how do you make a process to achieve any goal? Then next, how do you apply this some kind of strategy to bug hunting? Then this new fuzzing style I've been kind of developing. Some other people out in the industry have been working on. And then finally, how does this all tie back to Chrome IPC? So also, just to mention, I should mention that the bug I'll be showing in this presentation was used in a full chain exploit that I developed with a couple other people. And the details of the exploitation of that will be discussed at OffensiveCon. So that's also here in Germany, and hopefully people check it out. So how do you become an expert at anything? And I kind of was thinking this before I even started anything, and I was like in the CTF stage. And I was just kind of curious, like if I approach this with the mindset of there's this arbitrary skill I want to learn, and if I approach it strategically, like what's going to happen? So I looked into this expert research, and then there's kind of this idea of pop psych, like you need to study something deliberately for 10,000 hours to get good at it. And there's some debate about this number. It's kind of made up, I guess. But the essential idea of deliberate practice, I think, is very useful, and it's exactly how I structured my studying. And so what deliberate means is when you're learning, you want to be thinking like purposefully, like I want to make sure that the project that I'm doing is making me get better. I want to be actually thinking about how I'm structuring my training. And then you want to make sure that you're kind of always struggling, because that's just how you're growing. So essentially, to do this, you just need to keep picking projects that have some like success and failure feedback mechanism that's tied to the real world. And with bug hunting, like this is very obvious. You're either finding a bug or not. And like as I mentioned, you want something difficult but achievable. And so this kind of order that I did the different projects I mentioned in the beginning was like specifically chosen so that each stage would be achievable to me, but also like really, really stretching what I could do. And there's a funny anecdote. There's this guy named Ben Franklin from American history, and I read the story that he used to be really bad at writing and wanted to get better. So the way he did it was he took an essay that looked perfect to him, and then he took notes on it, and then a week later he rewrote the essay from the notes, and then he would just compare the goal versus what he had done, and basically saw all the shortcomings. And so that kind of just stuck in my head, and so I'll show like how do you apply this kind of trick to bug finding practice. And then just another thing with setting goals for bug hunting. A lot of it is psychological. I think it's almost psychological more than intelligence, like for sure. And basically, you want to iteratively pick harder and harder projects so that your tolerance for failure goes up and up. And so by the time I was working on Chrome, I worked on it every day for 6 months, like right home from work until 1 a.m., sleep up, and then all day every weekend, and found nothing the whole time. And then just one day found something. And then from there, all that accumulated like struggle and effort, when the bug precipitated, it was just like a sign that all these like necessary skills were there, and then I was able to repeat it. And so, so now I'll talk about what that actually looked like for bug hunting. So when you think about how to train this skill, I think there's kind of two constituent skills that are important, and those are knowing where to look and then recognizing the bug when you're looking at it. And this first part is just from my own experience, it seemed like just being a developer, it's pretty easy to get a sense for, you can look at the Git logs, like I'm mentioning here. Are there crashes happening somewhere in the library? Are bugs getting reported, publicly? Does the code look bad? It's not hard to tell that something looks sketchy, but I think what's really hard is getting the bug to kind of come out. And so that's where I'll talk about strategy kind of directly. And so I kind of have this training idea where essentially once you have this kind of target in mind where it's a little bit out of your skill range, but you think it's doable, you try to enumerate all the existing bug reports and then look through each of them. And then it's this like Ben Franklin idea. Like you take the bug and then you look at, usually there'll be like, this block of text and they're mentioning like the file where it's happening and stuff. And you can kind of skim it and sense like where the bug is. And so we know without actually looking at what it is. And so then you go over and you try to find it yourself. And it's really important that you actively try to look for the bug yourself and kind of strain yourself. And when you've given up, essentially, then you look at what was the bug, and then through that struggle, it's usually pretty clear like what was the fundamental thing you were missing, and just by repeating this process constantly, this is how you train. And so this is actually how I first ever started on bug hunting. Was some of you may know Yuru. He's this like really talented researcher. He's been at it for a long time. And I remember seeing this blog post from him showing all these IDA Pro bugs, and it just kind of blew my mind. Like, wow, someone took IDA and found like security vulnerabilities in it. And then when I looked at the bug reports, they're pretty small. So I thought, okay, how do I practice, and how could I have done this myself? So basically the first day, they're all like integer overflow bugs. I could barely even, I knew what integer overflow was, but I hadn't like actively looked for it before. And so, I was looking at the function and I couldn't find it. And basically I went to sleep feeling like, oh God, like I'll never be able to do this stuff. And then the next day I looked at it again and I was like, oh yeah, that's actually easy. And then kind of failed the second one, and then kind of by the third day, I was like able to just see where they were once, I knew where to look. So that kind of made me think, okay, I'll just keep doing this for a long time and keep doing harder and harder. So this is essentially the strategy. Like, I think, I'm probably the perfect example of someone who's like an intermediate CTF player, really like insecure, whatever, like, and just wanted to get into this, but I had no idea what I was doing. And I just kept thinking, if I just believe in this kind of process, hopefully it works out. And so here's just like a little really basic roadmap if you want to try to replicate what I did, which is to focus on CTF, because if you can do CTF binary problems, these are perfect examples of a kind of training where you try to do something yourself, there's a write-up. And like once you can do these problems, all the kind of low-level details that are needed. You know what a bug is, things like that. And then from there, you just kind of progressively do harder and harder targets. And so there's kind of this component where, like, you can't really assess your own ability, like how much of this is innate or something. And it just seemed to me that regardless of that, this. Like I'm saying here, this isn't chess where you have people like trained from birth with like perfect study and like decades of, like we're barely figuring this stuff out, and it's just kind of a huge mess. And so there's plenty of room for new people to join in. And then also like there's a lot of these kind of stories about people who are just insanely naturally gifted and stuff. And I tried really hard to like look into what these people are actually doing, and I haven't found a case where someone wasn't working extremely hard. And so, just keep that in mind. So just for the sake of time, I won't go into this too much, but if you're looking at the slides later, I just kind of give more detail on like how I picked the mini projects and got down to Chrome. Now let's talk about fuzzing. And so before I get into it, I should emphasize that you should really know how to do auditing. And the first couple of years, and like not until into that 6 months of failure on Chrome, I was doing auditing the whole time. And I think fuzzing gets a bad rap because people think that these are unrelated strategies, and people are only a fuzzer person or an auditor person. And really, I think these things are extremely, they work really well together, but you can't really know why fuzzing is failing or how to even apply it or where to apply it without being able to audit yourself. And part of this was like I noticed on Chrome that I could audit things, but essentially the bug density was so low on the sandbox attack surface that I needed a way to kind of automate what I was looking for in each subsystem I was looking at. So you have like 20 subsystems that you want to read. Well, it takes about a week each minimum to learn. It's a lot faster to try to fuzz for like a day or two each thing, and then I don't know. Like I can't explain it. It just did random things, and then this is what worked. So, so how would you practice fuzzing? It's really the same idea that I had about auditing, where you take a bug and just ask yourself, like, how would I have written a fuzzer in the first place to hit the bug? How could I have known to write the fuzzer that would have triggered this? Am I lacking something in auditing ability? Am I not able to write fuzzers well enough? And it actually took me probably like a year of fuzzer writing to get good enough where I could actually act on my ideas. Like, just it's kind of tricky. And so we'll get back to it later, but this exact idea of practicing fuzzing on something that looks unfuzzable is how I found this real exploitable sandbox escape. So really quick, just for those of you who don't know too much about fuzzing, at least in like the current meta, essentially there's this tool called AFL that came out in 2014, which I think really shifted how well fuzzing worked. And the idea is essentially that you have some corpus of inputs that you want to fuzz, and then as you're mutating them, you're looking for coverage feedback, which is compiled into your code. And then as you're mutating and running new test cases, when you find new coverage, you take that input and put it in your corpus. And over time, your corpus kind of grows and grows as more coverage is hit. And so there's this just seems to work really well. And then there's another version of this, basically called libfuzzer. And this is just written by the LLVM project. And the same people who wrote Address Sanitizer also wrote libfuzzer. And just in my experience, it's written in a way that's a lot more extensible and like easy to understand and play with. And so it makes it kind of easier to audit and fuzz together. And so if you want to think about what fuzzing is, essentially you're trying to replicate the normal testing process, but kind of parameterizing like what a unit test would be doing with some input bytes that you're just feeding into something and seeing if it crashes. And so what's interesting is there's kind of this gap in the middle of like an end-to-end test, which AFL will give you, just feed a binary, or like the unit test, which libfuzzer will give you, where you just keep stuffing bytes into a parser. And real security vulnerabilities are kind of logical in nature. And I think that's why people think that fuzzing isn't applicable. And I think there's actually kind of this part in the middle where if you see a few components that look suspicious, and then you can integrate them and fuzz them in isolation, but have the complexity that you'd kind of see in a real program, that's where a lot of bugs come out. And so how we do this is using grammar. And so essentially it's combining generative fuzzing with coverage-guided fuzzing. And so we'll touch on how that works in a minute. But just for some more evidence on why does this work well, like I'm not the only person who is doing this. Kind of simultaneously, myself and two other people, I guess, seem to have stumbled across this idea last year or 2 years ago. And those are syscaller and LokiHeart. So syscaller is a kind of fully automated Linux kernel fuzzer. And if you guys haven't seen this, it's kind of hilarious. Like, essentially, they are automatically generating zero-day bugs, like tens per month at least, and they automatically generate the test case, like submit the report. When the commit comes in, it's like automatically tracked. It's basically this zero-day generator sitting there. And yeah, no, and I see this, I'm like, okay, there's 3,000 bugs that are being found. there's a web app for it, and you can just download it, you know. And I saw the Linux talk from the author of Syscaller, and the YouTube video has like 100 views and stuff. I'm just like, okay. So people need to, I got to reiterate how important this stuff is. So then there's Loki Hart as well, who's like a famous, extremely talented, kind of canonical auditing fuzzer person. And he seems to be doing a very similar thing with Chakra and V8, and he's finding like tens of interesting exploitable bugs. And then there's me, who applied this on the Chrome sandbox and found over 30 bugs, about half of which are security relevant, and then 5 of which were like sandbox escape without render code execution. So you know, this is just to emphasize, like, we're finding really important things with this technique. And since I discussed this the first time a couple of months ago at POC conference, it's been used by someone in the Chrome security team to fuzz SQLite, and they're already finding new bugs like in the first week. So just more of the evidence, like here's the kind of the breakdown of some of the bugs I found with this strategy. Just to highlight a couple of them, or maybe 3 of them. So the first one was like an out of bounds read, just an integer overflow in blobs, and this lets you, you can make a blob and then ask to read part of it, and then the offset could have been negative, and there's just an integer overflow. They got the check wrong, so it was a full like memory disclosure from the browser process. There's also this like app cache use after free, which is what I used in the exploit this year. And then finally, I guess the critical bugs are pretty interesting. So 2 of these, I guess the first pair are in Quick, and the first one is a stack buffer overflow with just a bad packet that comes in over the network. So you just browse to an attacker site, and they stack buffer overflow Chrome browser process, which is outside the sandbox, and it jumped over the stack cookie. So that was bad. And then these block file cache problems, these were in the HTTP caching mechanism, which is also in the privileged process. And these were actually crashing in the wild for 3 years, and they didn't know how to, I guess, I don't know if they didn't have resources or they didn't know how to address the problem or something, but I sent them the test case, and then they closed like 4 bug reports, you know, ancient bugs. So, you know, it just goes to show that this kind of technique works in the variety of really interesting places that are really important. And so now let's get to the boring stuff. So what's protobuf? Well, protobuf is this data serialization format from Google, and it doesn't really matter that it's protobuf. Just this idea is you want some kind of, you want to encode like a little language for yourself that expresses what you want to fuzz at kind of a higher abstraction layer than just fuzzing bytes randomly. And so if any of you have done functional programming, like I had been doing stuff with OCaml and like Quick Check for a couple of years, and then when I saw this, it was just immediately recognize the pattern. Essentially what you can do is you can create this little tree structure of just basic types like enum. You create these messages, and like you can just kind of specify actions you want your fuzzer to take. And then what this next tool, libprotobuf mutator, will do is it will take this specification you've written and link it into libfuzzer so that it will automatically fuzz and create these like trees that are you know, these kind of random ASTs from this little language you wrote, and then you can kind of parse this language, which sounds crazy or more hard than it is, but you essentially you can generate this highly structured input, which makes it a lot easier to explore like logical type of bugs. So yeah, just really want to emphasize that this strategy can be used to fuzz anything, and so kind of this same exact idea is being used to find bugs in like caching APIs, encrypted networking protocols, kernels, sandbox, like serialization code, stateful systems that have IPC and network interaction and timing as part of it, which is what we'll show at the end. And so like what's common here? We just fuzz all of these different systems in the same way. The idea is like as an auditor, what you do is you kind of notice like, okay, there's some subsystem, like some caching mechanism with a simple API, and you look at how it's implemented and it looks complicated, so you think, okay, if I can write a fuzzer in like a few hours for this, it seems like high value. So once you kind of play with the API a bit and understand like how the API works, you can just write this little specification for the API in protobuf and go ahead and write the fuzzer. So basically, I'll show how this works on Chrome. So just to make sure I cover all of kind of the background knowledge, for those of you that don't really care about fuzzing or don't care about anything else, at least you can get bootstrapped on Chrome IPC research. The basic idea of how the Chrome sandboxing situation works is when I'm saying I'm finding bugs in the sandbox, like it's really finding bugs in the browser process which are reachable from a sandbox process. And so the sandbox itself is just constraining these render like tab processes, so they can't really do much. And then what you want to do is kind of jump from there to the browser process, which can do anything. So it's a very common model, like almost, like on 3DS, you have like userland, kernel, then security code processor. You have on Linux, like you might have a userland process. And then in the sandbox, there's some APIs in the kernel you can hit, like syscalls you can hit. And basically everything just keeps boiling down to, there's some API that you can look at from the less privileged context. And then if you can trigger a bug in that API, you escape, and then you just kind of, this kind of applies everywhere. And so this idea of understanding like self-contained chunks of like, the syscalls in Linux are like hundreds, but being able to look at and say like, okay, here are 10 related syscalls. This is like a subsystem that I want to fuzz in isolation. Like this is kind of how you want to think about it. And so if you just want to get started on Chrome, what you want to do is look at, okay, what are these endpoints in the browser process that I can reach from the renderer? And then you don't really have to understand how IPC works to do this. You just have to be able to recognize where, what you're allowed to hit from the renderer to the browser and what's actually in the browser. And so fortunately, the Chrome code base is pretty well organized, so they just tell you. If you just generally go into any folder that says browser in it, like all of this is outside the sandbox and prone to sandbox escape. And so most of my bugs I found were in this content browser subsystem kind of thing. But you can look anywhere, and I think like all these results I've had the last year were just like in one folder, and so there's so many other places where bugs can manifest that I didn't even look at. So basically, there's plenty of room for more. So just to go in on what I did is in this kind of content stuff is you just want to see where kind of the APIs that are reachable from the render are enumerated, and those are in this render processed host impl init function. So yeah, like C++ is kind of wordy, but you get used to it. Basically, there's two places where the APIs are set up and or the interfaces are exposed. Those are create message filters and register mojo interfaces. And it took me a while to realize where these were, like a year or something, but like those are the key functions to look at. And so I'll skip over old style IPC because it's going away, but it's pretty easy to figure out what's going on if you look at it. So I'll talk a bit about Mojo. So essentially, this is a new IPC kind of platform that the Chrome team has developed. And the idea is they want to, I guess, simplify this process for developers in terms of defining a interface that you want to expose to a renderer or some other client somewhere else. And Essentially, you write these little interface files called .mojam, and then the build system will generate all the C++ glue for you that you can just like subclass something, and then it handles all the mechanics of actually exposing this to other processes and so on. And so as a security researcher, you don't really care about that. All you care about is like, what can I reach, and how do I know like what to fuzz or something. So what I guess I looked at is just, what are some of the Mojam files that have that are subclassed in this content/browser, and you can just do a little grep to check this. Essentially, the app cache was one of the bugs I found this year, and here's the API that the renderer can. These are all the messages that the renderer can send to the browser, and along with the types of the arguments. And so, that's pretty straightforward. So in the browser process, this is the code that we're trying to attack, which is the actual C++ like implementation code for this API. And so you can see their subclassing there, and then they just make sure to override all these virtual functions that actually implements the API. And so I won't go too into detail on this part because it's a little boring, but essentially, how does the renderer get from it to all the way over to this kind of browser C++ code? Well, it essentially goes through this like request mechanism where the renderer tells the browser process like, hey, I have this kind of request to access this interface, and then it'll actually just create that like dispatcher host implementation object, and just feed in that request over there. So essentially, stuff gets glued together somehow, and then there's this stuff, which is kind of ugly, but I mean, here's where you're actually exposing the ability to do this. So here's where we're actually like the request comes in, and then where this kind of request handler function gets fed in is that thing I mentioned earlier, the register mojo interfaces. So it's named pretty well. It's kind of easy to follow. And they're adding new stuff constantly. All of this stuff is on the attack surface. Like I think, I stopped Chrome a couple of months ago. I think I looked, and there's like, 5 new APIs in there or something. Like they're just constantly adding things. So just a quick point about this. Essentially, you want to do fuzzing in process with this like libfuzzer protobuf mutator strategy, and you don't want to be like actually doing IPC, and like it's just very brittle and weird. So what you really want to do is just like, here's the C++ object. I want to just instantiate it and call those functions myself, and then this whole thing is just very lightweight and easy to play with, which is having a lightweight and like very easy to rebuild, tweak something, and play with it, print things, like kind of the faster you can iterate, the better. So anything that's too complicated, like the success rate goes way down. So essentially, like the fuzzer that I made open source is like the way you should do it, but the way I actually did it was I just like made the object, like commented out the private, like I don't know if you can see it on here. Yeah, so just like commented out private, created the object, started calling these things randomly. It would crash, and I would just hand fix things, and it's kind of sloppy, but you're testing something in a very small unit that's not really exposed to that kind of testing. So now let's kind of put together everything I've talked about so far. So this exploitable app cache use after free I found this year was found using this same idea of deliberate practice. So I looked at this app cache subsystem in the browser process, and I noticed that there were 3 old bug reports that were triggering memory corruption. And they were pretty interesting because they involved different kind of ways of attacking. And these things had clearly been audited. And I had actually seen these bugs a couple of years ago, and I kind of used it as evidence to myself at the time that fuzzing doesn't work and you need auditing. But it kind of stuck in my head, and I kept thinking someday I'll come back to this and like I'll overcome it, you know? And so essentially what's interesting is, you know, I've already talked about, you know, it's easy to specify the API and just feed IPC messages into it. And I think, you know, everyone kind of understands that who does any IPC fuzzing. But then there's also this idea that you've got some remote server that the app cache thing like creates a network request. Some server is, you know, serving that request and doing different things. And so in the second bug, it actually matters when things were, like when the server was returning data, because some jobs like stay alive, and then if you send an IPC message to, you know, close your session, and then the job is still alive, there's like a raw pointer somewhere, and you know, something going on that it matters that the server keeps the connection open. And then the last thing is just kind of a logical issue, and if the server returns these HTTP codes in the headers of the response in this kind of weird order, you trigger some logical bug that actually leads to memory corruption. And so, you know, I looked at this and I said, okay, well, so what do we need to test to cover all this? Basically, IPC network and that timing. And so, not only that, but this is kind of a stateful thing. So we want to make sure that for each fuzzing session that we kind of reset the state completely. And fortunately in C++, this wasn't too hard because you know, you just destroy the object, and if it doesn't exist anymore, what state is there? So, you know, you just make sure that like you don't leave things lingering. So yeah, so I just had this basic idea. We'll call random IPCs with this fuzzed input. We return random data from the network, and then we reset the state of the cache on every iteration. And then part of it was thinking, okay, like if I can repro these old bugs, if I reintroduce them by editing the source, this is kind of appealing to this like deliberate practice idea that like I could have written a fuzzer that would trigger these old things. And this is kind of the idea I was pursuing when I actually triggered a new bug. So now what's tricky about this is if you just return random data from the network, you're not going to make much progress. And this is kind of where the auditing background comes in, is you know, you want to think about what is expressive enough of, like how do I make my fuzzer expressive enough that I can hit everything, but then not so generic that it's just spraying, like it's just noise. And so I'll show how I did that in this specification. And so at a high level, my kind of root node in the AST or the tree of the fuzzer message is this session message. And then this just contains a sequence of commands. And so commands are something I also made up. And so the first 10 of them are all the different IPC calls I can do. The 11th one is handling any pending requests or pre-caching like a response to any new request that comes in. So that handles like both the asynchronous case where it makes a request and it's waiting for the server, and also like the synchronous version where the response comes immediately. And then lastly, this run until idle thing, which essentially just it helps you, like if you kind of place these run until idles randomly as you're kind of doing these IPC messages, you're kind of flushing the queue of accumulated work. And so what this lets you do is kind of identify these race condition type things, because you can do something like do a bunch of IPCs that come in and are handled at the same time without like actually serving, like actually doing the work yet. And then you do this run until idle, and then like all the work happens. And you know, I didn't like think of this a priori in some like smart way. I just looked at like the unit tests, and I just tried to think about like, okay, how are these developers already testing it? And this is just what it looked like they were doing. So these messages are very easy to write. Essentially, just provide for each IPC message that I could have sent to this thing, just make sure all the arguments are correct, and then there's a little bit of cleverness, which is like the host ID is also breaks down to just an enum of like 0, 1, 2, because just from looking at the code, you know that if I'm randomly creating hosts, destroying them and stuff over the whole 4 billion int 32 IDs, like it's just going to fall apart and not find anything interesting. So I just constrained that. For the URL, that is also a custom message that I constrained to just return a few like pre-made legit URLs, so that way I'm also not testing like the URL parsing stuff. So then, how do I handle the network? Well, I just read the source and looked at what are all the types of HTTP response codes that affect control flow, and I just enumerated them, and then for any given request that comes in from the app cache system, I kind of just encode anything interesting about the response that I thought of just by reviewing the source. And it seemed like the things that mattered were those HTTP codes, whether or not the headers asked app cache to do caching or just download it once. And then also, the app cache can request from the server this manifest file, which has some metadata about what files that it should be caching. And so, essentially just all of this is encoded in one message. And so how you go from this like high-level description to actually fuzzing is just this. So you can see how simple it is. You're really just I looked at kind of the unit test code and saw how they set up this app cache service. And so they let you pass in this URL loader factory. And what this is just this kind of unit testable network request thing. So this is how I'm like, intercepting the network requests and feeding data. And so I do this little setup. And then here I just create the one like renderer to browser host. This is just kind of simulating how you would do the Mojo stuff if it was a real the real renderer to browser interaction. And then I just go through those commands that I mentioned and just do these things. So this is all it is. You just pull the host ID out of this protobuf message that we're getting at the top there, that session that I defined as like the top level tree node. And you just go through and you just call the APIs that are there. And so how to get the network stuff to work, as I mentioned, I have this like mock URL loader factory, also C++y, but essentially it's this, so this is when I basically handle one of my request messages that I came up with. I just simulate a response. This is a built-in like unit test function that they have in their code base. And I just pass in the relevant bits that came from that message. So so this is what it looks like. I have some kind of do request helper function, and then I just pass my stuff through to it. And so it takes that like URL factory and then serves responses to anything that's waiting. And then what's interesting here and what's necessary to find the bug is that, I mentioned that this is asynchronous. So what will happen is when you do like register host, and then if I go back, you like register host, select a cache, do some things like the app cache will make a request to the server, and then get this manifest, and then it will start making requests to download things, and then these things are like pending. It's pending like responses that it's waiting for from the server, and so it actually mattered that you mutate the state further before those responses come in, and so by doing this like in between the IPC messages, not like preloading the network factory with a bunch of responses, I'm actually like serving things like I'm not encoding an assumption about when I'm serving responses. And this is kind of tedious to go so into detail, but essentially, you run this thing, it's maybe 150 lines or something, and then trigger this bug with address sanitizer. And so essentially a use after free happens, and what's going on here is you can see the scoped ref pointer destructor, and it turns out that let's see here, so when you go to unregister the host, like it's an IPC, that's an IPC message there at the bottom that I sent, and then it just accidentally, this is kind of inaccurate, this stack trace, but essentially some ref count goes from 1 to 0, and then it starts destroying this app cache object. And then in the destructor, one of these kind of requests was waiting on a response from the server, and then it essentially like gives a reference back to that other object. And that's kind of aligning some details, but essentially like the ref count went back up to 1, and then now you're adding a bunch of references all over the place to something while it's being destroyed. And so what happens is now you have all these pointers to a freed object, and then you can trigger access to that freed thing again later. And so this is kind of the recipe for an exploitable bug. And so I just wanted to point out that all of this fuzzer is open source, and it's just in the Chrome code base. So if you download it or go online to the code search tool, you can just search for app cache fuzzer, and it will come up. So then real quickly, just to kind of cover the exploitation, I guess I have more time than I thought, so I compressed this a lot. But essentially, I did this in part in a chain with 2 other guys, Salo and Nicholas. And so Salo provided the RCE bug, and so from there we get code execution in the renderer, and then this lets us send arbitrary IPC messages. And so it's kind of annoying to send IPC with Mojo like arbitrarily, so we kind of piggybacked on the renderer side, like glue code for sending these app cache messages. So we just like found the C++ object and called into it. And then all in all, we end up with this primitive where we can dec ref and like release reference to this ref counted thing like after it's been freed multiple times. So there's 2 stages to exploiting this. Like, because we're in the renderer and we only have 1 bug, we need to turn this into a memory disclosure. And so fortunately this bug can be triggered repeatedly. And so the idea here is triggering it once gives you this decrement by n primitive. And so when you're releasing, if you ever hit 0, you'll trigger the destructor again. And so essentially what you want to do for the leak is to not trigger the destructor because it will blow up, but rather find a string somewhere in memory where there's a string pointing to the heap, and then decrement the string pointer, so then it starts like sliding somewhere else into the heap, so that when you read that string back, you're actually leaking heap data. And so we did that. So there's some object that had a standard C++ string in the beginning. On Windows, the first keyword is like the pointer to the string data. So we decrement this. It was actually a cookie object, so we just read the cookie back from the browser, and then in the cookie value we see the leaked bytes. And then from there was a vtable access that we can control in the destructor. So we make another fake object that looks like it has 1 reference left, make it hit 0, so destructor is triggered, and then this app cache thing gets confused and essentially calls a controlled vtable pointer. And then from there, those are the primitives you need to write an exploit, and then it was just a matter of kind of putting it together. And if you're curious about that, again, you should look forward to Nicholas's talk. And so just a summary, essentially, starting all the way from the beginning, you want to be practicing deliberately, keep working constantly, and keep identifying gaps and actively working to improve. Which it sounds weird, but you kind of want to keep that in mind. and use this new technique with libfuzzer and protobuf mutator. I can promise you it's not going to be the last time you see someone using this. And I mentioned I've started on XNU, and we'll see some initial results pretty soon on that. It's working. So yeah, and lastly, never give up. Just may take months, but it's fine. So with that, I guess I'll open to questions. Yeah, thank you.
Thank you for that talk.
Sure. Yeah.
If you do have a question, please line up at the microphones in the room and try to limit your question to one single sentence. If you would like to leave at this point, please do that as quietly as possible so that everyone else can still stay for the questions. And also, if you're listening on the stream, you can ask a question online to this. Seems there is no question. There is one. Microphone number 2, your question, please.
Hello.
Hello.
I just wanted to ask, why have you chosen Chrome for bug hunting? Was it just like you picked one random browser and then started?
Yeah, no, I mean, it's basically just kind of the hardest thing I could think of that I could plausibly do, you know, just for the purpose of getting better. And so there's more to it. Like, I think Chrome, the way it's written, is very amenable to research. And like, I actually didn't know C++ before I worked on Chrome. So like looking at a great example of a C++ code base and learning from that was really helpful to me. And you know, I glossed over kind of my path, but I was actually finding random, like, obscure, like, library bugs that weren't even reachable at first. So just the quality of Chrome makes it so that what you're training is the real talent, not just like being able to decipher bad code. So yeah, highly recommended. I can say that, like, I definitely feel that the 2 years I invested on that one project, like, completely helped me get better. So yeah.
Thank you.
Sure.
Single angel, question from the internet.
Hello. There is one question from the internet. The question is it possible to attack Chrome IPC via hardware vulnerabilities like Meltdown or Spectre?
So the question is it, I guess, possible to attack using Meltdown or Spectre? So I don't know. I guess it's possible. I was essentially focusing only on kind of application level bugs, so things that I could trigger, like, kind of deterministically, using only bugs in the Chrome code itself. And so, I mean, also those things came along like way after I was doing my research. So, you know, I can't comment on that, but I'm sure someone knows.
Thanks.
Yeah.
I see no more people on the microphones or question on the internet. Yeah. Okay. Thanks for your talk and thanks for Q&A.
Thank you.